ladies and gentlemen, our honored guest too, Professor Adam from UGM, and my colleagues from UGM also, and all of the HATI members and the webinar attendees today. It's a privilege for me to welcome you all in this webinar. It is organized by the Hydraulic Associations of Yogyakarta, and also with us, Center of Excellence for Water and Climate Resilience. These occasions, we are really grateful. It is the second webinar we have in this month, and we are so thankful that we now have our speakers to join us, Professor Daizo Suzumi from Shinshu University in Japan, and also Professor Yutaka Gonda from Niigata University, also from Japan. And we are having a theme, the topic of this webinar is sediment transport, monitoring and management in volcanic river basins. It is really interesting, especially for us also, because we are here as Sabo Technical Center is a working unit under the Ministry of Public Works who works with the sediment related disasters, specifically development of Sabo engineering technology. Dear participants, we are grateful for this collaboration, and this event is also a testament in the role of Center of Excellence for Water and Climate Resilience as established during the World Water Forum, the 10th World Water Forum in Bali in 2024. And this is also as one of our efforts to become a hub for Sabo engineering technology development, and also resilience against water-related disasters and climate impacts. This webinar is more than a specific scientific exchange. It is also a platform for collaborations, bringing together researchers, practitioners, and policymakers who share a commitment to advance knowledge and developing practical solutions in terms of sediment disasters. By combining the local expertise of HATI Yogyakarta with broader visions from the speakers we have here, the expert, we are building bridges between science and society, between research and actions. Dear participants, ladies and gentlemen, over the course of today's program, I encourage you all to engage actively, to share your insight, and also to explore new ideas, because we have, I think, a really competent speakers here. Let's use this opportunity not to only deepen our understanding of the sediment dynamics, but also to strengthen our collective capacity to manage water and climate in this challenging extreme condition right now. We are finally thank for all of you, for the committee, for bringing this this webinar, and we hope that we can have a better, good conversations. And with that, I think I'm really delighted to open this session. And without taking much time, I think we can just directly start with the webinar. So I ended with Billahi Taufiq wal Hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir, for the opening. For today's presentations and discussions, I will hand it over to our moderator, Mr. Santosa Sandiputra, PhD. The time is yours.
Good afternoon, our distinguished attendance to this webinar. Thank you very much for your enthusiasm to learn more about the risk behind the existence of volcano. As we know that Indonesia is located in the ring of fire with around more than 100 volcanoes. Yeah, active volcanoes, some of them. And this afternoon we have a special guest, a distinguished guest from the University of Niigata in Japan. We have Professor Yutaka Kunda. He got his PhD from the University of Tokyo, and his research interest is about the erosion control. And we also have Professor Sutsumi Daiso. He graduated from the University of Kyoto, and his research is about hydroengineering, especially for mountainous area like that. So we will start the discussion this afternoon. Probably we try to bring a new insight. Yeah, as we know, some of us is having a Ramadan fasting these days. So we also want to say happy Ramadan fasting, and hopefully this afternoon discussion will be a joyful discussion and not so stressful. Yeah. So we will try to bring more interaction. And for example, for those who attending online, please during the presentation, don't be hesitate to raise your inquiries or your questions, your ideas through the Zoom chat. And later on, we will try to have a dialogue with you if you don't mind to also deliver your question directly to these two distinguished guests. Please don't wait. You can just type it in the chat room, and later on we will try to filter and we'll try to call you to probably have a good interaction. For the first occasion, we will have Professor Yutaka Kunda to present. Hopefully it will be 15 minutes, sir. Yeah, and the more time we will use for interaction with the audience in Zoom. Yeah. For Professor Yutaka Kunda, the time is yours. Thank you very much. Yeah.
Dr. Santosa, thank you very much for introducing me, and it's my great pleasure to have to be here and have a good opportunity to deliver our talk relating my current research topics.
While waiting for the operator to present Professor Kunda presentation, in the morning we have a chance to visit
Light one.
the right one. Yeah.
Balai something.
Okay.
So name of my file is MSD 2025.
Not this one.
Not this one.
Okay.
I'm sorry. Oh, this
that
this
one. Yeah.
Got it.
Yeah. So while waiting, we have a chance to visit Merapi River Basin this morning. So we visit Bebeng River, and Professor Gunda and Professor Susumi also provide some interactive comment. So related to current condition, especially related to this the morphology of the river, and also the interaction between the river development and also the local people activity there, like sand mining and then agriculture and everything. Probably some of you may ask many questions related to the current challenge for volcanic disaster monitoring later. Professor Gunda, please. Yeah.
Thank you very much. I'm Yutaka Kondo from Niigata University, Japan. Today, I will be talking about my research topics, relationship between hydraulic conductivity and volcanic ash deposited thickness in Arimura River Basin, Sakurajima Volcano, Japan. Okay, next. So, most of you know very well, so occurrence of lahar in the volcanic area are strongly controlled by the condition of the surface of the ground. And for example, when a volcano have been inactive for a long time, so hydraulic conductivity of the ground surface is rather high. In such a case, most of rainfall can infiltrate into the ground and no surface flow occurs. But once volcanic starts its activity and a large amount of volcanic ash supplied to the mountain slope, and which covers the surface, and the hydraulic conductivity of the surface drastically decrease. And in such a condition, next please. In such a condition, most of the rainfall cannot infiltrate into the ground, and the remaining part of the rainfall, which cannot infiltrate into the ground, generates surface flow, and the surface flow can trigger the lahar. So what I want to say now here is risk of lahar is depending on the mainly on the total amount of volcanic ash covered with the mountain slope. So, please next. To assess, it is very essential to assess the risk of lahar to mitigate the lahar disaster. But to do so, we must know exactly what surface condition trigger lahar. But so to know what surface condition, the best way to know surface condition is direct measuring in the field. But actually, it is not easy to do so because surface conditions are easily changed in the active volcano, and because field survey in volcanic areas are very dangerous. So to grasp the surface condition, temporal changes of surface condition, which may trigger lahar, we have to develop some kind of indirect method. Next. So for assessing temporal changes in slope surface condition indirectly, we developed two models. The first one is estimation of the hydraulic conductivity of the slope surface using rainfall runoff models. And the second model is estimation of residual deposited thickness of volcanic ash. So using these models, we discuss relationship between hydraulic conductivity of the slope and the thickness of ashfall on the ground surface at lahar event in this study. Okay, so I'd like to introduce my study areas. So my study area is Arimura River Basin, which is located southern flank of Sakurajima volcano. So Sakurajima volcano is one of active volcano in the world. And so Sakurajima volcano produce a much amount of volcanic acid every year. And within Arimura within Arimura River Basin, there's several monitoring equipment installed. For example, at the blue circle point, there is ash gauge, and the yellow point, there is ultrasonic water level meter and water velocity meter installed. Okay, next. So I'd like to introduce the methodology for estimating hydraulic conductivity using rainfall runoff models. So in this study, so kinematic wave method is used as employed as rainfall runoff simulation models. In this method, for the river basin shown on the left, divided into sub-basin, and at each sub-basin, simply modeled like model. Do you have pointer or something like that? Okay, so I will continue. So each sub-basin model very simply to calculate surface discharge, surface runoff, and each surface runoff from each river basin routed along the drainage system of the river basin, and finally we obtained the rain runoff discharge at the outlet of the river basin. So topographic data which is necessary to calculate rainfall runoff models, we create it from DEM by using GIS. And the rainfall data which is necessary to calculate is created using X-rainfall. X-rain is a kind of product X-band rainfall products produced by the Ministry of Construction Japan. So I'd like to calculate surface runoff of each sub-basin. We introduce two-layer slope systems. In these systems, surface of the ground was consists of two parts. The first part is top layer is a volcanic ash layer, but this layer is very thin. Below this layer, there are solid layers. So we set different hydraulic conductivity at each layer. And in this calculation, if rainfall exceeding the hydraulic conductivity will flow out as a surface runoff, but rainfall below the hydraulic conductivity will infiltrate into the ground. Okay, next, please. Okay, I'd like explain how to evaluate of hydraulic conductivity of the slope in this study. So this figure illustrates a measured height graph and calculated height graph with different hydraulic conductivities. So black line indicate the measured hydro graph, and the blue line indicates calculated hydro graph using hydraulic conductivity 10 millimeters. Red one is using hydraulic conductivity of 50 millimeter, and the green one is hydraulic conductivity of 20 millimeter per hour. So as you see this figure, peak, please look at the here, peak discharge. If we choose smaller value of hydraulic conductivity, so peak discharge becomes greater. I mean, hydraulic conductivity value directly affect the value of peak value of the hydrograph. And so compared with these three calculated height graph and measured height graph. So red one, calculated hydrograph with a high 10 millimeter per hour of hydraulic conductivity seem to match best. So therefore, looking at the as a result of comparison of the waveform of measured hydrograph and the calculated hydrograph, we decide that representative hydraulic conductivity of the current station is 15 millimeter per hour. In this manner, we evaluate hydraulic conductivity at every Lahar event. Okay, next, please. Okay, I will next explain the how to estimate the residual deposit thickness of volcanic ash. So to do so, we developed erosion deposition models. So this model can estimate the temporal changes of residual depths of volcanic ash like this. So please look at this figure. Black line indicates the residual depth of the volcanic ash. And please look at here. And the blue line indicates the occurrence of Lahar. So if Lahar occurred, so residual depth of volcanic ash decrease because decrease. And please look at here. So residual depth of the volcanic ash increased because new eruption occurred. So in this, using erosion deposition model, we can estimate the temporal changes of residual depth of volcanic ash, considering erosion by the occurrence of Lahar and the deposition of newly fallen volcanic ash like this. But please next. To construct this model, we have to consider the two things. The first thing is how to estimate the upstream asphalt thickness from downstream asphalt gauge, because we have only asphalt data here. Therefore, we have to evaluate based on the asphalt data here using this data, and we want to know the estimated volcanic ash depth around here. Here is the source area of Lahar. So based on the previous study of Dr. Fujimura, so it was found that there is a clear relationship between distance from crater center and the elevation change by the deposition of volcanic ash. According to his study, we can estimate the elevation change at any location from the crater using this figure, this equation. So by applying this equation at here and here, we obtain the result that the volcanic ash
thickness at the upstream area is 7.28 times more than the automatic asphalt gauge. So therefore, we decided to use this equation to estimate asphalt thickness of upstream area by the asphalt thickness at the automatic asphalt gauge. Okay, next please. So, so another thing we consider is how to erosion rate of the volcanic ash by the occurrence of surface flow. So erosion rate equation used in erosion deposition model is we choose these equations proposed by Dr. Tamura, which is proposed for estimating erosion rate at the Miyakejima volcano. But to use this equation, we have to know this parameter h, flow depth on the slope. To know, to evaluate please next. To evaluate h, to estimate h, the height of the flow, surface flow at the upper ridge areas, we employed this equation. So to derive this equation was derived from Manning formula under the two important assumptions. The first assumption is surface flow occurs only this area. And the another assumption is so discharge from the upstream area is almost same as the outlet of the drainage areas. By employing two assumptions, we can obtain this equation to evaluate height of the flow. Okay, next. Okay, let's move on to result. I analyzed the 55 Lahar event from 2015 to 2012. And so among these, shape of the waveform was the hydrograph of 41 Lahar event can successfully be reproduced by our models. But remaining event, we cannot reproduce hydrograph with our models. Okay, next. Then we discussed based on the hydraulic conductivity, we can succeed to reproduce the waveform of the hydrograph. Okay, this figure illustrates time series comparison of asphalt thickness. The green line is asphalt thickness, and the black dot is hydraulic conductivity at each Lahar event. So as you see this figure, shape of these figures, so the beginning of this year is 2020, so residual asphalt thickness gradually increasing like this because of the deposition of newly formed asphalt. But from here, you can see 1, 2, 3, 4, 5 dots are plotted during this period. It means we had 5 Lahar events during this event. Due to the occurrence of these Lahar events, erosion occurred as a result, residual thickness decrease like this. And as you see, the shape of green line and the distribution of black dot seem to synchronize each other. Okay, next slide. Okay, this figure was drawn. This figure illustrates the between residual asphalt thickness and the hydraulic conductivity. But all the total of 55 events are separated for each year. But looking these figures, you can easily find the decreasing trend. There is a decreasing trend at each year. But comparing the data at the 2015 and the 2016 and other years, so slope of depression line become changes between this year and this year. I mean, the slope become more negative after 2015. Okay, next. So why slope of the depression line changes after 2015? So one possible reason for that is a influence of crater activity shift. So please look at this figure. Yellow polygon represents the drainage area of Arimura River Basin. But the northern edge of Arimura River Basin, there is two craters. So this one is the Showa crater, and this one is Minamidake craters. And please look at this figure. This figure illustrates the number of the eruption of each craters. As you see, before 2017, so Showa crater is very active, but after 2018, so Minamidake crater become active. I mean, crater active shift changed. So I guess, we guess, the reason why depression line, slope of depression line changes because caused by the crater activity shift. When crater activity shift, so fine grain of the fine portion of fine volcanic ash increase after 2018. As a result, hydraulic conductivity tend to decrease even at small deposited thickness after 2018, and slope become more negative. Okay, next. So I'd like to conclude my presentation. That is summary of my presentation. Thank you very much for listening. Please give a round of applause for Professor Gunda. Thank you very much. If I may to make a short summary in Bahasa, Professor, yeah.
Okay.
So because many of the audience is they're using Bahasa for their daily activity, ya. So dari presentasi siang hari ini, Bapak Ibu, mohon izin Profesor Gonda berusaha menunjukkan fakta, data-data dari Sakurajima Volcano di Jepang, di mana ada pengaruh antara hydraulic conductivity, yaitu kalau bisa dibilang sederhana itu tentang kemampuan tanah untuk mengalirkan air. Demikian, Ki. Habis, Profesor. Ada kemampuan tanah meresapkan air hujan, dan juga ketebalan dari deposit atau dari ketebalan dari abu vulkanik di lahan gitu ya. Jadi ada dua faktor penting yang Bapak Ibu bisa highlight dalam suatu letusan gunung api, di mana kedua faktor ini yaitu hydraulic conductivity dan ketebalan dari abu vulkan ini mempengaruhi discharge atau debit dari banjir lahar atau aliran lahar yang akan terjadi gitu. Jadi Profesor Gonda summarized that the hydraulic conductivity uh, will decrease when the volcanic ash thickness increase like that, yes, Professor. Volcanic ash thickness increase, hydraulic conductivity will decrease like this ya. Oke. Jadi berarti kalau ketebalan abu vulkanik itu tebal, jadi letusannya membawa material vulkanik yang cukup banyak, itu kemampuan permukaan tanah untuk menyerap air hujan pada saat terjadi puncak dari rainfall itu akan menurun begitu. Jadi hasil riset dari Profesor Gunda adalah ketika abu vulkanik semakin tebal, hydraulic conductivity-nya semakin kecil, itu berarti air akan lebih banyak mengalir ke sungai daripada menyerap ke tanah. Demikian. Jadi Bapak Ibu pengelola sungai River Basin Authority yang mengelola area sungai vulkanik perlu diperhatikan juga ya untuk monitoring di activity itu ketika erupsi vulkanik itu misalnya terjadi di musim-musim misalnya kemarau di mana aliran ini mengendap dengan banyak ya, jadi semakin tebal selama musim kemarau tidak teralirkan. Itu nanti ketika akan ada musim hujan, kecenderungannya air hujan itu akan langsung mengalir ke badan sungai gitu ya, daripada mereka akan meresap dulu. Tapi kalau misalnya erupsinya terjadi di musim-musim hujan ketika secara rutin endapan abu vulkanik itu terbawa aliran, itu kecenderungan ada kemampuan dari watershed, dari das itu untuk bisa menahan sementara dari aliran banjir yang akan terjadi. Kira-kira summary-nya seperti itu, nanti Bapak Ibu bisa review lagi ya presentasi dari Profesor Gunda. Kita lanjutkan dulu, monggo Bapak Ibu kalau ada pertanyaan bisa disampaikan di Zoom, nanti panitia akan pilih. Kita minta untuk resen untuk bisa berinteraksi langsung dengan narasumber kita. Thank you very much Profesor Gunda for your presentation. We are waiting for the response from the audience. Right now there are around 250 audience watching for our presentation through Zoom ya. While waiting for a response, we would like to give the time for Professor Sutsumi Daiso to also present about the new insight related to the volcano risk monitoring in Japan and in international, I guess ya. Please take your opportunity, Professor. Thank you. Yeah.
Okay, thank you for introducing me. I'm Daiso Tsutsumi from Shinshu University, Japan. Today, I would like to talk about the development of a sediment transport measurement method. This is a new method in terms of using electrode plates in mountain rivers. Okay, as you all may know that the sediment transport monitoring is very important and also essential in mountain rivers for the sediment control within the whole watershed or the risk management against landslide disasters. So last several decades, we tried to monitor the sediment transport in the mountains river. And mainly in European countries, they use this kind of devices, which we call Swiss plate geophone. by this sensor, when the sediment collide on the plate, which is fixed in the riverbed, it produces seismic signals. And to monitor this kind of seismic signal, you can measure the bedrock transport rate. But this one is a kind of indirect method to monitor the sediment movement. This is one example of the installing the Swiss geophone plate in one of the mountains river in Switzerland. And as you can see that these are the array of the geophone plates. And also, because this is an indirect method, you need to parallelly conduct direct monitoring methods. In this case, they employ the moving basket sampler. And from these different methods, you can make the correlation between the indirect signal and the direct bedrock discharge. Okay, and in Japan, we also developed different type of the devices, which we call it Japanese pipe microphone. By this sensor, when the sediment collide on the steel pipe, which is fixed in the riverbed, and which produces acoustic signal, and from this acoustic signal, you can know the amount of the bedrock discharge. Again, this is also the indirect method. So, okay, this is an example of the installation of Japanese pipe microphone in the mountains river in Japan. This one is a pipe microphone. And also, parallelly, we need to conduct the direct sampling method. In this case, we use the slot sampler. From these two signals, we can know the better discharge from the indirect acoustic signal. But there is a big problem by this equipment. You can see that the figure shows this figure shows after the very large sediment movement event. This device can be destroyed by gravel impact very easily. Therefore, they have the problem of not being able to measure the amount of sediment movement during the most critical large-scale events. So you can see that the pipe is completely deformed by the impact of the large sediment impact. Okay, and also Swiss geophone plate can be destroyed by the high-speed bedrock discharge. So we need to improve or solve these problems. One approach to solving this problem is to make the devices more robust. And you can see that one is example is that not using the pipe, using the plate, or increase the thickness of the pipe floor. And another approach is to keep the devices from contacting into coming into contact with the sediment as much as possible, which is a kind of contactless method. We install we install the electrode plates on both sides of the channel and apply the alternative current voltage. And when the sediment flow between the plates, we expect that the current will decrease due to the resistance will increase. So we employ this contactless method and try to develop the new sensors. I will explain again the measurement principle again, and we install the voltage here, and this is the electrode plate area, and this one is the distance between the electrode. Therefore, we calculate, the electrical current depends on these three factors. So we calculate sigma here, which is divided by the current, by the voltage here, and electrode plate area, and multiplying the distance between the electrode. This sigma is the electrical conductivity itself. So we can measure this, we can calculate the electrical conductivity from the measured value of the current. And well, here the area of the electrode is which is the width of the electrode and water level. Okay, and another thing is to explain is that the electrode current won't flow in a rectangular solid area like this. Instead, we think it flows in an area that has spread out horizontally like this. Therefore, we define the apparent electrode plate width like this in this way, and set the ratio to the actual electrode plate width as R like this here. And using this ratio R, the electrical conductivity sigma becomes like this. So this one is the actual electrical conductivity value. Okay, and then at first we conducted the water tank experiment using this kind of rectangular water tank and installing the electrode plate both sides of the tank. And the dimension of the tank and the electrode is like this. And we found that the sediment concentration and electrical conductivity has a very clear linear relationship like this. So when we measure the electrical conductivity here, we can know the sediment concentration very clearly by using this equation. Okay, so then next we have conducted the flume experiment like this. The length of the flume is 1.8 meters, and we supply the sediment from the upmost part of the flume. And here we install the electrode plate in the both sides of the flume. And this one is one of the example of the experiment. Here we can see the current meter, and this one is the voltage meter, and this one the EC meter. Okay. As you can see that sediment flows between the electrode, the current value changes depending on the sediment. But the voltage doesn't change, and also the EC value doesn't change as far as this condition of the experiment. Okay, and the result, I can show you the result here. The top figure shows the temperature change of the water level, and the second figure shows also the temperature change of the current. And third figure is temperature change of the calculated EC value. And fourth figure is the ratio of the calculated EC value to the measured EC of the water. And the bottom figure shows the result of the temperature change of the sediment concentration. And this pink background shows the duration which the sediment passing between the electrode plates. And as you can see that the water level and also current changes, and that result of the increase of the sediment concentration like this. So this figure shows the relationship between the supplied volume of the sediment and vertical axis shows the measured value of the sediment volume. And as you can see that, we changed the volume of the supplied sediment for 3 cases, and each cases we do this experiment 3 times. And the red circle indicates the average value of these 3 results. And you can see that the supplied sediment and measured, which means the calculated volume of the sediment, shows a very good correlation. So from this result of the Plume experiment, we think that this method can be used for the sediment transport monitoring. So finally, we tested this method in the field, which the place is the Hodaka Sedimentation Observatory, Disaster Prevention Research Institute, Kyoto University. And this photo shows the installation of the electrode plate on the experiment, the field channel. And this figure shows after we install the electrode here, both sides of the channel, and we also install the water level gauge here, and also we install the EC meter, which measures separately, but not independently from the electrode method. And which measures the EC value of the water itself. Okay, I will show you the one of the example of the measurement result. Left figure shows the highest graph. In this case, rainfall continues about 6 or 7 hours, and highest rainfall intensity is only 8 millimeter per hour. So it means this rainfall is not so intense one, very average rainfall. And the right figure shows the water level change from the top, and EC value. Red line indicates the calculated one, and blue line indicated the measured EC value. So from this 2 EC value, we can calculate the ratio of the EC, and which from that ratio, we can calculate the sediment concentration on the third figure. And bottom figure shows the sediment discharge ratio, sediment discharge rate, which is the sediment concentration multiplied by the water discharge here. And you can see that during the water level increase, sediment concentration increase, and also the sediment discharge increase like this, and the peak is almost same as water level peak. And these 2 figures shows the comparison between the sediment discharge calculated by this method, and also the hydrophone response, which is measured by the Japanese pipe microphone. And as we can see that, that hydrophone response is pulses per minute. So this is not the actual sediment discharge, but you can see that these two figures shows very, very similar trend. So maybe this method can calculate sediment discharge as well as Japanese pipe microphone. However, you can see that the maximum value of the sediment concentration reaches to 0.2. I think this rainfall event is not so very big. So the sediment concentration 0.2 is overestimating. So now we are trying to find out the reason why this method overestimates the sediment concentration. And we think that one of the reasons is that the electrical current not only flows within the river water, but also flows in the concrete, riverbed concrete. So we try to find out that assumption is true or not. We conducted a physical model experiment using making the a model of the Hodaka plume, concrete plume, like this, and have done the experiment like this. The scale is 1/10, and we measure the water temperature, water depth, and the EC of the water, and also current. And yes, we have conducted 3 experiments. One is no electrical isolation to the electrode, which means that this electrode installed directly to the concrete wall here, like this. And second condition is that only the electrode is electrically isolated, which means that we install the rubber plate between the electrode and also between rubber plate, electrode and concrete wall. And the third condition is that total isolation, electrically isolation, which shows we install, first we install the rigid seat to the whole plume and install the electrode on the region. Okay, and then I will show the result here. This bottom plot shows that total isolation result, which means that depending on the water level increase, the electrical current also increase, and which shows a perfect linear relationship. But when you do not have the isolation at all, the current is much higher than this result, which indicates that the current does flow not only the river water, but also in the concrete. And in between this relationship, this plot shows only the plate was electrically isolated. So which shows a little bit higher than this linear relationship, which indicates that even though you install the plate behind the electrode plate, the current flows within the concrete through the river water. So from this result, we recommend that the recommendation is that total isolation is necessary to have this kind of simple relationship. So now we are thinking that we will, how to say, isolate whole the flume using kind of lava steel or paint on the concrete flume itself. So I will try this next coming rainy season. Okay, so this is my conclusion so far. Thank you very much for your listening. Thank you.
Thank you very much, Professor Susumi. It's a really interesting presentation ya. If I may explain it in Indonesia ya, in bahasa saya. Ya, jadi Bapak Ibu, rekan-rekan kita bisa lihat bagaimana. Before that, Professor, would you mind to show the slide when you compare between you compare the electrical and the mechanical ones, sir. You compare the two results between not this one, sir. The one that slide number 10 probably. Yeah. When you present two different results, yeah. Next, again. The result. Okay. Yes. Yeah. Next. Again, sir. Yeah. The one that with the next. Continue to the end. Yeah, please. Next. Yeah. Next. Yes, this one, sir. Yeah, you compare the electrical method and the pipe microphone method. Yeah. So we would like to, before that, would you mind to answer, do you register this invention as a patent, sir? Do you register this invention as a patent? Patent is like a brand or something that intellectually registered in the law, like that. You have the authority of the inventor of this. Okay. No patent. Okay, yeah. It's because it's really interesting in Indonesia right now. The academician, the people in the university, usually they are expected to have patent, like intellectual property, like that, yeah. And if your research is in Indonesia, probably it's one of the it will be nominated for patent, like that, ya. Ya, jadi Bapak Ibu, kita bisa lihat bagaimana kolega kita dari Jepang mendevelop suatu teknologi ya, monitoring aliran lahar. Saat ini kita nggak tahu ketika ada aliran lahar karena biasanya kita melihatnya secara visual. Jadi kita minta tolong kepada warga yang tinggalnya dekat dengan sungai untuk melihat kira-kira sekarang banjir atau enggak gitu. Banjirnya tingginya berapa dan segala macam gitu. Jadi kalau di Jepang rekan-rekan develop teknologi itu karena mereka memang sekarang populasinya sedang decreasing ya, sedang menurun gitu. Jadi Bapak Ibu bisa melihat gimana suatu teknologi itu didevelop dari laboratorium scale ya, dari skala laboratorium pakai flume seperti itu. Setelah kira-kira hasilnya dapat, mereka coba ke physical model yang lebih besar ya, skala lebih besar di saluran, demikian. Mereka terapkan instrumen-instrumen monitoring dan sekarang baru setelah itu diterapkan di lapangan, demikian. Jadi Bapak Ibu bisa lihat bagaimana physical model, hydraulic model ini, terutama Bapak Ibu warga HATHI ya, ketika Himpunan Ahli Teknik Hidrolik Indonesia. Itu jadi selain ada mathematical model, kita juga ada physical model. Jadi kalau Bapak Ibu ada yang saat ini mulai mungkin bertanya sebenarnya physical model itu kepake nggak sih, akurat nggak sih, gitu, susah nggak sih, dan ternyata rekan-rekan di Jepang ini masih pakai physical model gitu ya, selain untuk didampingi dari numerical model gitu. Dan kebetulan dari Balai Sabu ini, Sabu Technical Center, kita punya lahar laboratori ya. Jadi laboratorium lahar berdasarkan beberapa testimoni atau pernyataan dari tamu-tamu, itu salah satu laboratorium lahar terbesar di Asia Tenggara gitu. Jadi kalau Bapak Ibu kolega yang akan memiliki interest, terutama warga HATI, untuk explore more about hydraulic model, bisa join di Sabu Technical Center. Kita support, dan juga dalam kerangka Center of Excellence for Water and Climate Resilience, dan kebetulan ada Ibu Kepala Lab di sini, Bu Hana juga. Itu laboratorium hidrolika kita termasuk laboratorium hidrolika yang terakreditasikan gitu ya. Jadi nanti Bapak Ibu kira-kira kalau ada interest untuk bisa riset seperti rekan-rekan kita yang di Jepang gitu. Saya ingat, jadi kalau dari presentasi Profesor Sutsumi ini kan bagaimana beliau mengubah dari yang mekanis, jadi yang dulunya itu impact, jadi batu-batu, kerikil, debris itu dia impact ke sensor dan baru terdeteksi kira-kira debitnya berapa gitu. Tapi kelemahannya adalah cepat rusak gitu ya, kena impact batu itu rusak gitu. Nah, Profesor Susumi dan laboratorium berusaha mengembangkan pakai elektronisasi gitu ya, jadi pakai elektroda untuk mendeteksi aliran debris ini gitu. Karena kalau pakai elektroda kan lebih lebih awet karena nggak kena impact langsung dari debris gitu. Ya, dari sini dites skala laboratorium sampai di skala prototype gitu kan. Jadi monggo nanti Bapak Ibu, teman-teman juga terutama insinyur-insinyur muda ya, Gen Z gitu, yang suka ngoprek-ngoprek elektronik, mekanik gitu. Ini di-challenge juga nih dengan Profesor Sutsumi. Kira-kira nanti ditunggu karya-karyanya terkait dengan teknik sumber daya air gitu ya. Sensor-sensor apa yang bisa rekan-rekan Gen Z Indonesia. Kalau senior kami di Balitbang dulu cerita kan, orang Indonesia tuh kreatif-kreatif gitu ya. Jadi alat-alat yang teknologi luar yang nggak ada manualnya itu bisa dioprek di sini, jadi bisa jalan gitu. Spare partnya nggak ada, tapi teman-teman Indonesia ini sangat kreatif ya, terutama anak-anak muda ini dioprek sendiri, diperbaiki, dan akhirnya bisa jalan gitu. Teknologi asing dipakai di Indonesia ini mungkin ke depan, kalau pesan dari Bapak Ibu senior dulu, amati tiru modifikasi gitu ya. Jadi monggo para teman-teman Sivitas Hidrolik Indonesia bisa, siapa tahu dapat inspirasi di sini, nanti dimodifikasi dan bisa menjadi suatu produk yang siapa tahu bisa dipatenkan gitu ya. Suatu yang membanggakan bagi seorang peneliti maupun praktisi teknik sumber daya air. Kira-kira demikian yang bisa saya summary-kan from Professor Susumi presentation. It's really interesting, and the result between the electrode mode and pipe microphone is quite similar ya, and it's very very promising for future development like that. And as I promised earlier when we start the discussion, we would open wide as possible to all the participants to interact directly with the speakers with this special occasion. Hopefully you will have a chance to directly deliver your question, your ideas in these communities. Please, would you mind to raise your hand for those who are available in Zoom? You can directly deliver your question. From the chat is already there is a question from Rizky Anugrah S. To Rizky, would you mind to also deliver your question directly to Professor Susumi? You can raise your hand so our operator can provide access to your camera, if you don't mind. And we also waiting for another response. While waiting, so for the second announcing, Rizky Anugrah S, will you mind to interact directly, or otherwise we would like to also we just read your question, yeah. To Susumi Sensei, in both flume experiment and field tests, does sediment concentration result can separate the trend between fine sediment and bigger size sediment? Yeah. Yes, please. Yeah.
Well, okay, thank you for your question. As far as we know that we cannot, how to say, separate the grain size. The sediment concentration includes fine sediment and coarse sediment also. But there's one problem is that when the sediment size is very, very fine, like the silt or clay, which affect the electrical conductivity increasing. So we need to know the critical, how to say, the size which increase the electrical concentration or decrease the electrical concentration. So that it is another challenge for us, yes.
Okay, Professor Susumi, so you try to validate risky question, yeah. So there is still a research gap, yeah, that probably if you want to continue studying the subject, study with Professor Susumi, yeah, in Japan, yeah, related to how to differentiate between a bigger size sediment and finer size sediment related to the sensitivity of the sensor, like that is there's still a big chance for all of you who want to also study about this subject, yeah. While waiting for the response, another response, are there any comments or response from the audience in the auditorium? Okay, Professor Adam, please.
Thank you very much for the time. First of all, I like to appreciate the presentation. Post presentation is very great for us. I have a question for Professor Kunda related to the change of slope. You hypothesize, you guess that because the shift of the crater, right? So then I'm interested about the spatial distribution of the asphalt on that catchment area. Is that influence to your measurements or to your model? How you assume the assumption about that the spatial distribution? So that was the first. Or directly, okay, please. But I have another.
Okay.
Okay, please.
So regarding the spatial distribution of asphalt, we have currently no data. Therefore, and not only spatial distribution, but also the quality to the grain size distribution of the volcanic ash we don't have. Therefore, so what I said in my presentation is currently an assumption or our idea, so which is not validated yet. So, but So if we succeeded to evaluate the spatial distribution of the dead volcanic ash from the ejected from the crater, we can evaluate, we can validate that our finding is really true or not.
For your answer. And the next question for Professor Susumi. It is interesting, this idea to measure the sediment transport through the conductivity of the water, and you found about the effect of the bed conductivity, and then you try to isolate these sensor with isolation is like plastic or glass or something, and non-conductive or still conductive. That's what my question. So the isolation means to stop the conduction, or I don't know. But my thinking is, I think is because you use alternating current. Usually in the conductive methods, for example, measuring the water depth or waves, it use direct current for conductivity method, but for using dielectric, so to measure the change of the current of alternating current because of dielectric of the media between two sensors. So it use not the conductivity but the dielectric, the electrical field, the wave of electrical field. So if it use isolation, that means no longer measure conduction, but measure the electric, the alternating limits, the effect of the electric field from the sensor to other sensor. So my interest also about the frequency of the alternating current, because if the frequency higher and higher, maybe it's different thing happen. So like in radio, this is antenna, like antenna, because the we know it's no longer using conductivity, but using the resistance to the electric field propagation. So that's what my thinking about this, because I'm interested in, and also in this instrument, like maybe. Thank you very much.
Okay, thank you, Adam Sensei, for your question. And I'm afraid that I understand your point 100%, but I will try to explain. Well, I think my explanation is not enough about isolation. So again, I show the drawing here that shows the three different cases of electrical isolation. Left figure shows no isolation, which means that the electrode plate contacts directly to the concrete wall. So as I was not, I have no idea that the current flows through the concrete, but it is very common thing. It is common thing, not only through the river water, but also through the concrete. So without isolation, the current flows like this. red-colored area. And but the contrary, when you isolate whole the plume, which means that the electrode between the electrode and the concrete wall, and also the river water and the concrete bed is isolated like this. So only the current only flows through the river water. Yes. So this is a ideal condition. So I hope from now on we would like to isolate whole the plume like this. But so far now we only isolate the electrode between electrode and the concrete wall. But in this case, actually the current does not flow to the concrete wall, but through the river water, the current is flowing wet concrete. So this is not ideal condition. So we hope that the total isolation is necessary. Yeah.
Okay, thank you very much. Now I understand because I thought the isolation is between the plate and the water.
River water. No.
Behind it.
Yes, behind the
the convection still works between two plates
between the
water.
Yes.
So because you use alternating current, so my question is the effect of frequency.
Okay.
For example, 50 hertz for the 60 hertz or maybe 100.
Well, yes.
Do you vary it?
Yes. Thank you very much for your further question. And yes, we have actually tried to find out the effect of the frequency of the current. And we found that it depends on the electrical current depends on the frequency. But when the frequency goes over 1,000 hertz, and the current become constant. So we employ the frequencies about 1,000 hertz. 1,000 hertz. Well,
it has effect.
It depends on the frequency. When the frequencies decrease, the current also decrease. So, which I'm not sure what is the reason why, but when the frequencies, again over 1,000, it become constant. So we employ the frequency 1,000. Yes. Thank you.
Okay, thank you very much, Professor Adam. So you highlighted more about the space for development about this instrumentation. Yeah, hopefully many students are motivated to explore more about this so that we can improve our early warning system in Indonesia. Yes, sir. Yeah, especially we have a lot of more than 100 active volcanoes, and if we don't have early warning system, it will be very risky for the people to improve the economy in that area. Hopefully many people are interested to develop more. There is a question from Professor Budi. To Professor Budi, would you meant to deliver your question directly, or you want me to reread your question?
Okay, I can try to ask by myself. I have some measurement about the sediment concentration with electric conductivity, but in my experience, we that the high concentration measured and high EC, electric conductivity. But here I saw in your presentation that during high flood, the EC is lower. Yeah. So can you explain to me what is the measurement, of the concentration or something else? I don't know. Thank you. In the slide, there is when there is a high flood and the EC is lower.
Lower. Okay, so I will show that result again.
Next slide, perhaps.
Okay.
Your curve.
So you mean this one? So could you ask me?
Yeah, that's
again?
one.
Yes.
Yeah.
So you mean the EC value decrease like this?
Yeah.
Okay. Well, I think that first of all, this method, principle of this method is to calculate the sediment concentration from the difference between the measured EC value, which is water EC, and the calculated EC value, which is measured from the electrode, measured electrical current by electrode plate. So from this difference, we can found the sediment concentration. But your question is that why the EC value not only for the calculated value but also the measured value decrease during the event, right?
Yes.
Okay.
The lower. I saw the sediment concentration is higher at that times, but the EC is lower.
Yes,
Yeah.
EC become lower. The reason I think the reason why the EC value are becoming lower during the event is that because the EC value of the rainwater itself is lower than the the water flowing out from the soil layer or the bedrock layer, which has a high silica concentration, and the rainwater has a lower EC value. So during the rain event, the water become less conduction.
Okay.
Making myself clear?
Yeah, but because in my experience, normally we measure the electric conductivity in the water that's carrying the sediment. Yeah. So we also measure the sediment in the water that we measure the electric conductivity.
So you mean from your experience during the event, the EC value increase, right?
Yeah, during I mean when there is a flood and there is a high sediment concentration, and the EC is higher.
I see. Okay, I think
before they carry the sediment.
Okay, I see. I think it's true, but in this case, I think the event is not so big, so not too many sediment is conducted in this water. So the effect of the rainwater is higher than the effect of the turbid water, I think.
Okay, thank you.
Thank you very much.
Thank you very much, Professor Budi. There is we need more data. Yeah, we need more measurement. We need more experiments to answer this. Probably something that might still arguably between researchers, but Professor Susumi has concluded that probably because the concentration of sediment is quite low, the EC is showing like this. But probably if we conducted more research, we will understand deeper about this phenomena. Yeah. The next question is from Mr. Muriatin. Would you mind to deliver your question directly? Mr. Muriatin from Haluoleo University. While waiting for Mr. Muriatin, is there any more questions from the audience in the meeting room? Okay, if not, so I will try to address the question from Mr. Muriatin to Professor Susumi. How do you detect very strong current and coarse sediment materials using your instrument, especially related to the durability and accuracy of the electrode plates? So, yes. So how your instrument can detect when the environment is having strong current and coarse sediment. Strong current is high discharge, and coarse sediment load like that, yeah. So do you recommend application of your instrument to this kind of environment, or you need or we need more modification to your instrument so that it can be implemented in an area where there are very strong currents and coarse sediments? Yeah.
Okay, thank you for your question. And so far, we have never tried such kind of condition in the real scale field. But in the laboratory experiment, we have conducted the effect of the discharge or flow rate. And we found that there is no effect of the, dependency of the flow discharge or flow rate to this method. So I think when you conduct real scale measurement in the field, this system can detect high current and also coarse sediment. But again, you have never tried such kind of condition, so we need to evaluate further. Yes.
Thank you very much, Professor Susumi. So, Mr. Muriatin, there is still a chance for you also to contribute in the development of this instrument, especially for the area in the east part of Indonesia where there are a lot of rivers with very strong currents and coarse sediment, sediment load, So please don't be hesitate to conduct correspondence with us for future development. So in the end of the meeting, we will have some insight as well. As I mentioned earlier that in the morning, Professor Gonda and Professor Susumi had a chance to visit some rivers in Merapi area, and I would like to present to you in a very brief about current early warning system in Merapi, So So if you can see my screen, right now we have a critical line monitoring. Yeah, this system is operated in Volcanic Sabo. It was developed. It was developed by Gonda Sensei, Makoto Shimomura-san, Yamane Kaizuki-san, and many researchers from Indonesia, Mr. Ahyar, Mr. Indra, Mr. Bananta, yeah. So we have a monitoring for lahar flows. As you can see now, we have a critical line monitoring. Right now it's real time, yeah. So for example, you can see here we have a sensor in Pabelan River. And right now in the Jeraka station, rainfall occurs, yeah. And we have the data like here, even though we haven't validate it sufficiently, but at least the system is work and it provided a critical line of rainfalls from our stations. So there are 3 lines. If the rainfall line crosses this line, it means warning for lahar flow like that. But of course, the validity of this information needs continuous data, yeah, because this is a data-driven model. So hopefully, if there are students out there and many practitioners that want to explore more about lahar flow critical line and warning system, the chance is still widely open, yeah, like that. For further development of monitoring related to the sediment hazard, please don't be hesitate to come or contact our correspondence with Balai Teknik Sabo. And if you want to explore more about the success story of river basin management in a volcanic river, you can also correspond with Balai Besar Wilayah Serai OPA, and we have around 277 sabodams here. So field study and everything is very welcome with Balai Wilayah Sungai Serai OPA. Thank you very much. With that note, I would like to conclude to finish the discussion session this afternoon. If you still have many inquiries or questions or ideas, please don't be hesitant to contact us through email or Instagram. We will deliver your questions or your insights to the appropriate respondent and also to Professor Gunda and Professor Sutsumi. Yeah. By that, I will return the moment to the MC, Ms. Kiska. Thank you very much. Yeah.
Okay, thank you. Ladies and gentlemen, that concludes the session of our webinar today. But before that, we will have a closing remarks from Ms. Vicky. So Ms. Vicky, the time is yours.
Thank you for your great presentation, Professor Yutaka Gunda and Professor Deizo Susumi. As we are coming on our second collaboration with the Balai Sabo or the Sabo Technical Center, we are happy that this has been very fruitful discussions, and also we had many interests coming from online sessions, and many students also are interested in the activities that we are doing with this joint effort. And today we learn more about how hydraulic conductivity and as deposit from the volcanic activities is happening in Rimura River Basin. We have similar activities here with Merapi River and Merapi and their rivers, and your study also maybe initiate our interest in going into further knowledge on how we see the rivers that has Merapi as their upstream, and there is of course connectivity between the rain precipitation level and also the eruption, and how much water will come and make lahar to flow. And in each of the rivers this might be different, and hopefully there will be interest coming from our participants today to do further collaboration research. And also thank you, Professor Deiso Susumi, for the explanation about the development of electrode plate methods. We don't have that right now, and maybe it will be an interesting idea to start making pilot projects in Yogyakarta also. So just to keep us in the spirit of collaborations, and together with this insight from both of your presentation, we see that disaster risk reduction does require a combination of advanced technology and, of course, adaptation on what we have in our river basin, especially the active volcanic river basins. We need also adaptation in structural interventions and different strategies for our watershed conservation. And by fostering this collaboration that we have today between researchers, policymakers, and communities, and also the students, we can transform scientific knowledge and into practical solution, and that will hopefully safeguard our lives and livelihood. And so, to close, I would like to capture the spirit of our shared mission in a haiku. Rivers carve their path, sediment flows, lessons learned. Rangers or rivers will rise. Thank you.
Thank you. Thank you, Ms. Vicky, for the closing remarks. So now we will have a documentation or photo group session. I will invite the offline audience here to stand up for a second. And for the online participants, I would like you all to please open your camera, and our team will screen capture it. Thank you once again for joining us. I would like to extend our sincerest gratitude to our honorable speakers, and I apologize for any shortcomings. Akhir kata, wassalamualaikum warahmatullahi wabarakatuh.